In section 1.5, we'll learn about the inverse of a relation. We'll see different ways to work with and interpret inverses, but generally speaking, we'll think of an inverse as undoing or performing the opposite operations in the opposite order of what's given. As an example, to walk into a room and turn on the lights would have as its inverse to turn off the lights and then walk out of the room. If we think of a mathematical operation, such as multiplying a number by 2 and then adding 3, its inverse would be subtracting 3 and then dividing by 2. Notice that not only are the operations opposited, but they are also performed in the opposite order. We could represent the first as multiplying x by 2 and then adding 3, and the second by subtracting 3 from x and then dividing by 2. So these functions could be considered inverses. In our first warm-up, we'll explore the relationship between the graph of a linear function and the graph of its inverse. We're given f of x equal to 1/3 x minus 2. Let's use the 6 x values given to generate some corresponding y values. As expected, the points generate a linear function with a slope of 1/3 and a y-intercept of -2. In order to generate the points on g of x, we will take the coordinates of each point on f of x and exchange them. For example, the point -6 and -4 will become -4 and -6. Note that the point -3 and -3 becomes -3 and -3. Because both the x and y coordinate were the same, when we exchange them, this has no effect. Therefore, this is an invariant point, as its location does not vary from the original graph. It turns out that the point -3 and -3 is the only invariant point. Connecting all the points, we find a line with a slope of 3 and a y-intercept of 6. We're now asked to sketch the graph of y equals x. This is a line passing through all points for which x and y are the same value. For example, 0, 0, 1 and 1, 2 and 2, 3 and 3, and even -1, -1. We note that this line seems to pass right between the two functions graphed initially, the linear function and its inverse. This is not a coincidence. We're asked here to compare the distance from the line y equals x to both the original f of x and transform g of x function. Now, the word distance might be a bit misleading here because the distance should be measured, typically, as the shortest, most direct line. But we're trying to show that this is a reflection about that line and hoping that you'll see how it is equidistant, as it were, from the line on either side. When asked to describe the transformations taking y equals f of x to y equals g of x, it would be easiest to use mapping notation. We were told to exchange the coordinates for each point. It makes sense then to describe our mapping rule as all points xy become yx. As noted in the previous slide, our invariant point was a point for which x and y were of the same value. That means the point will lie on the line y equals x, which is a collection of all points which have x and y as the same value. So we will list our invariant point of -3 and -3 but be aware if there were any other points for which x and y were of the same value, they would also be invariant. In Math 10, we learned about functions, and one of the criteria for being a function was that we could pass a vertical line test. What this means is, if we pass a vertical line over the graph, it will touch at most once. Note, if we scan this vertical line, that for both the blue or green line, it will never touch more than one point at a time. Remember, I'm not looking at both lines at once. I'm either scanning the blue or I'm scanning the green. What this represents is that for each point on the graph, each x value corresponds to at most one y value. There's no horizontal position that generates two different heights. When asked to determine an equation for y equals g of x, we can lean on our knowledge of linear functions and our slope-intercept form. Here we can see that the green line is rising 3 and running 1 for a slope of 3, and it's passing through the y-axis at the point 0 and 6. So in mx plus b form, we can say that g of x is equal to 3x plus 6. Remember our equation for f of x? Now, at first glance, you might not see the relationship between the two, but what if we rewrite this? Instead of saying 1/3 x, let's say x over 3. And instead of saying minus 2, let's say minus 6/3. We can now combine these two fractions, and the function becomes x minus 6 divided by 3. Note that these are the opposite operations in the opposite order when compared with g of x, where we are multiplying by 3 and then adding 6. This confirms for us that these two, in both an algebraic setting and a graphical setting, show themselves as inverses. The inverse of a relation is represented by y equals f to the negative 1 of x. It's important to note that this notation is slightly different than when we think of an exponent law with a negative 1. This does not correspond to 1 over f of x, the same way that x to the negative 1 would correspond to 1 over x. This is a specific notation that represents the interchanging of x and y, represented as the mapping rule of x, y becoming y over x. I repeat one more time, y equals f to the negative 1 over x is not the same as y equals 1 over f of x, which is the reciprocal function. Here we're given a graph of y equals f of x. Its inverse we found by exchanging all of the points' coordinates, so x and y become y and x. We notice here that while f of x was a function, g of x is not a function. For example, for the x value of 3, we have a point at both 3 and negative 1, and 3 and 3. Since one x value generates more than one y value, or since this would fail the vertical line test, this relation is not a function. If we follow one of our points, for example, negative 5 and negative 1, we see that its transformed version is negative 1 and negative 5. This corresponds to a reflection in the line y equals x. So all points could be considered reflections over the axis of y equals x. Our invariant points, therefore, will be all points that lie on the line y equals x. Here, y equals x intersects the graphs at 3 and 3. This is the only point for which both the x and y coordinate were the same. In order to determine the domain and range of our transform graph, we simply take the domain and range of our original graph and interchange them. For f of x, we see that the leftmost point was at negative 5 and the rightmost point was at positive 6. When we consider the transform graph, the inverse, we will see that it has a range going from a lowest point of -5 to a highest point of -6. Similarly, f of x's range was from -1 to 4. That will correspond to the domain of our inverse of the function. You may have noted that the title of this section is the inverse of a relation, and yet in many of our previous examples, we've used the word function. So what is the difference between a function and a relation? A relation is a more general term than a function. It describes a set of inputs that correspond to a set of outputs. This can be represented as a set of ordered pairs, an equation, a graph, an arrow diagram. These are all relations. A function is a specific type of relation in which each input corresponds to at most one output value. That is to say, there's never an x value that corresponds to 2 or more y values. Consider the relation of these 4 ordered pairs: -2 and 5, 0 and 4, 1 and -2, and 1 and 3. We can see that the input value of 1 corresponds to multiple output values. While this is still a relation, this means it is not a function. In our next example, we have the points -2 and 5, 0 and 4, 1 and -2, and 2 and -2. Though we now have 2 separate x values corresponding to the same y value, no single input maps to multiple outputs. Therefore, this relation could be considered a function. Modern graphing software makes it easier than ever to visualize relations and their inverses. Here, we'll show how we can use Desmos.com's online graphing calculator to represent the polynomial function y equals x plus 2 times x minus 1 times x minus 3 and its inverse. In a typical graphing calculator, unless we could isolate y, we'd be limited to graphing the original function and then asking the calculator to draw its inverse. Unfortunately, this would not allow us to use any of the calculating features or interact with the graph. Not so with Desmos. Here, we can understand that an inverse is the exchange of the x and y. So, for our second relation, we would type x equals y plus 2 times y minus 1 times y minus 3. And we'd see the two graphs as shown here. We can confirm these are reflections if we were to either graph the line y equals x, or just tilt our head to the right. We can see these graphs intersect at points where their x and y coordinates are equal. At this point, you're likely a wizard of the vertical line test and can simply look at a graph and say if it is a function or not. Often we'll be asked to determine if the inverse of a given graph will be a function. Rather than graphing the inverse, we can make use of the horizontal line test. Consider for a moment this first graph, f of x equals x minus 3 squared. We can clearly see that it is a function. However, that does not necessarily mean that its inverse will be a function. by passing a horizontal line over this, we see that it will never cross at more than one point at a time. Therefore, when we draw the inverse of this function and take a vertical line and pass it over, we will expect that vertical line will also never cross at more than one point at a time. However, in our second example, which shows a parabola, which is indeed itself a function, we see that a horizontal line will cross twice. Because of this, we will anticipate that the inverse will not be a function. Though we can confirm this by graphing it, it is not necessary. If a function fails the horizontal line test, its inverse will fail the vertical line test. Now that we have seen the inverse of a relation in the context of a reflection, specifically a reflection in the line y equals x, we have seen all three types of reflections that we'll see in this course. The first reflection we saw was a vertical reflection, or a reflection in the line y equals 0, or a reflection in the x-axis. This was represented by the original function of y equals f of x becoming the transformed function of y equals negative f of x. The mapping rule showed that all points x, y became x and negative y, as we multiplied each y coordinate by negative 1. A reminder that points on the x-axis, which is to say our x-intercepts, were the invariant points. Our second reflection was a horizontal reflection, or a reflection in the line x equals 0, or a reflection in the y-axis. This was the original function y equals f of x becoming the transformed function y equals f of negative x. The mapping rule of xy becoming negative x and y showed that each x coordinate was multiplied by negative 1. This meant that our invariant points were on the y-axis, which is to say our y-intercepts were the invariant points. Our third and final reflection is our inverse. This is a reflection in the line y equals x. We can represent this by y equals f of x, the original function, becoming x equals f of y, which may or may not be a function. The mapping rule showed that each point x and y became y equals x as we exchanged the coordinates. We'll note that in this case, our invariant points were those that lied on the line y equals x, which meant that both the x and the y coordinate had the same value. In class example 1.51, we will sketch the inverse of a function and describe some of its characteristics. I encourage you to try this on your own before clicking through. First, let's make a prediction on whether the inverse of this function will itself be a function. Well, though our original function does pass the vertical line test, it will fail the horizontal line test. This means that the inverse will not be a function. In order to graph the inverse, we take each point and exchange its coordinates. For example, the point negative 7 and 6 becomes 6 and negative 7. The point negative 6 and 7 becomes 7 and negative 6, and so on. We see here that we have one invariant point, which is to say one point that lies on both of the two graphs. This point will also lie on the line y equals x, for it is a point that has the same value as its x and y coordinate. In this case, the invariant point is 4 and 4. In order to determine the domain and range of our original function, we can simply identify the leftmost and rightmost points and the lowest and highest point. Here we see the domain goes from -7 to 8, and the range goes from a minimum height of 2 to a maximum height of 7. Remember, because we are exchanging all things x and y, our new domain and range will simply be exchange of the original here. So the original domain will become the new range, and the original range will become the new domain. In exploration number 2, we'll use Desmos graphing software to analyze the graph of a parabola and its inverse. To start, you'll need to visit desmos.com/calculator. If you set up your own account, you'll be able to save your graphs for viewing later. We'll start by inputting y equals x squared minus 4. And then, to input its inverse, we'll simply switch x and y. So we'll input x equals y squared minus 4 as our second graph. Note the two graphs produced. Let's analyze them. Can you recognize how their domain and range switch? For our original graph, we see that the parabola, as always, has an unlimited domain from -infinity to +infinity. Its range is greater than the height of its vertex, which is -4. For our inverse, we see that we have a sideways parabola. This has a range extending to -infinity and +infinity. However, the domain is now limited by the horizontal position of its vertex, which is to say x is greater than or equal to -4. Therefore, we can conclude the domain and range have switched as expected. We can also see that these graphs are reflections of one another about the line y equals x. While these two graphs are inverses of one another, they are not both functions. Our blue graph, which is the inverse, fails the vertical line test. This means that some x values generate more than one y value. If you haven't used Desmos before, it can be really powerful to help you visualize the work you do. I encourage you to try other examples and try to graph their inverses. One of the great benefits of the Desmos graphing software is that we can graph relations which are not functions. However, we can also do this in our graphing calculator with a little bit more work. In order to graph the inverse of the function y equals x squared minus 4, let's first write the inverse as x equals y squared minus 4. We've switched x and y. Next, we will isolate y. To do this, let's add 4 to both sides, and then take the square root of each. It's important that we remember to take both the positive and negative square root. Graphically, the positive square root corresponds to the radical function, or top half in red, and the negative square root corresponds to the blue radical function below the x-axis. Together, they represent the same as x equals y squared minus 4. So while we are able to graph both of these versions in Desmos, our graphing calculator would be limited to the lower example, where we would graph a y1 and y2 input. In our previous slide, we saw how the inverse of a parabola could be described as two radical functions, one with a positive a value and one with a negative a value. These made up the two halves of the sideways parabola. This time, let's start with a radical function and work with its inverse. This will be relatively straightforward on the graph, but has a bit of a trick when we look at it algebraically. We'll start by showing the graph of y equals the square root of x plus 5. This is your basic radical function translated up 5 units. Its inverse would require us to swap x and y. So we'll write this as x equals the square root of y plus 5. We see it in blue. Now, can we confirm that these are reflections over the line y equals x? By graphing the line y equals x in and tilting our head just a little bit to the side, we should see that these are both clear reflections of one another. Each half parabola, as it were, has its coordinates exchanged. So for example, the point 0 and 5 becomes 5 and 0. We'll notice that there is an invariant point around 8 and 8. It's a little bit shy of that, maybe 7.8, 7.8. This point lies on the line y equals x and does not change as we transform from the original to its inverse. Now, in order to determine the equation of the inverse, and in a way that we could put it into a graphing calculator, say, we would need to swap x and y, and then isolate our y. Here, after subtracting 5 from both sides, we will now square both sides to remove the square root on the y. However, this appears to give us a parabola, y equals x minus 5 squared. But we know that a parabola would have a right arm and a left arm, and the blue graph that we see here, the true inverse, should only be half of that parabola. In order to generate just half of the parabola, we will need to limit the domain. We'll do this by looking at what the range was of the original function. Originally, our red graph had a range of all values that were greater than or equal to 5. This means for our blue graph, the inverse, we will describe it as y equals x minus 5 squared, with x being greater than or equal to positive 5. Class example 1.52 asks us to determine both the graph and the equation for the inverse to this quadratic function. Now this example is like others we've done, so you'll likely want to try it on your own before clicking through the animations. Note that the original function is f of x equals x squared minus 9. This is a basic parabola that has been translated 9 units down. We'll first be asked to sketch the graph of the inverse on the same grid, and to make sure to indicate the transformed or corresponding points for each of the points highlighted with the dot. We know that the effect of an inverse is to map all points xy to yx. We see here that the inverse of our upright parabola is a sideways parabola. Notice that this graph will have invariant points, but none of them were the points that we plotted here. To identify the invariant points, it is easiest to draw the line y equals x. This is because invariant points for an inverse will always lie where the point has the same x and y coordinate. Here we see 1 in quadrant 3 and 1 in quadrant 1. Our original parabola, the one in blue, had a domain extending from negative infinity to positive infinity. Its range went as low as negative 9, the height of the vertex, and up to positive infinity. As we know, inverse relations will change the domain to the range and the range to the domain, because all things x and y are being exchanged. So we confirm with our green graph that the domain is from negative 9 to positive infinity, and that its range extends to negative infinity and to positive infinity. In order to determine the equation for the inverse in terms of x, we will first exchange x and y, and then we will isolate y. It is important to remember to include both the positive and negative square root here. If we forget the negative square root, then our inverse will be represented by only half of a parabola, specifically the top arm, so all things above the x-axis. Here, by including the plus and minus, we have graphed a relation which is not a function, but is the inverse of the original parabola. Having worked with some examples of parabolas, or radical functions, let's now go back and find the inverse again of a linear function. Here we're given f of x equals 4x minus 3, a linear function with a slope of 4 passing through a y-intercept of negative 3. Take a moment to sketch the graph of its inverse, state the coordinates of the invariant points, and then determine the equation for the reflected graph, which is to say the inverse. Let's first treat the reflection by changing all points xy to yx. Now, it's important to note, I've gone through this kind of quickly, but the reflection in the line y equals x is equivalent to the question saying, what is the inverse? Here, I've exchanged the x and y coordinates for the 4 points that were indicated. Really, any two would have sufficed, given that we're just graphing a line. In order to determine the invariant points, we can either graph the line y equals x, or in this case, just find the intersection point at 1 and 1. We see here, this is the only point for which the x and y coordinate are both the same. We're asked to determine the equation for the reflected graph, that is, the green line. Now, because it's a line, we have many strategies. We could determine the slope and use the form y equals mx plus b, subbing any point to find the b value. We could use slope point form, but here we're going to take the original equation, f of x equals 4x minus 3, and treat it as its inverse. After switching x and y, we isolated y. Because we got to y equals x plus 3 over 4, but wanted it to be an mx plus b form, we split this into two separate fractions. X over 4 plus 3 over 4. And x over 4 is the same as saying 1/4 x. So we see that the green line can be described by 1/4 x plus 3/4. A function is in many ways a rule that connects an input value to an output value. And on the first slide of this section, we said that the inverse of a function or relation was performing the opposite operations in the opposite order. So here, if we define f of x as multiplying x by 2 and then adding 6, its inverse would be subtracting 6 from x and then dividing by 2. What we see in all of the examples is that comparing the original function to its inverse, we find the same thing. Perform the opposite operations in the opposite order. After years of doing math, I've become very quick at performing the steps. But often in that quickness, I make little mistakes. Having a way of checking my answers like this is really productive. For example, knowing that if there was an addition in the original, it's probably becoming a subtraction in the inverse. And if there's a multiplication, it'll probably be division. If there's a square, it'll likely be a square root, and vice versa. This is a quick way to check your answers to see if they make sense. Class example 1.54 is an excellent opportunity for you to test your skills and build some confidence. Here, you're asked to determine the inverse of a radical function, which includes sketching the inverse, determining the invariant point or points, determining the domain and range for both the original and inverse, and determining the equation for the inverse. Let's start by sketching the inverse relation. Here, we will take each point on the original and exchange x and y. Our blue graph, which represents a radical function, has been transformed to the green graph, which is effectively half of a parabola. This transformation leads to only one invariant point, which lies on the line y equals x in quadrant 1. We see this is the only point where both the x and y coordinates were the same. It may be worth noting that if we needed to determine the coordinates of that invariant point, we could take the original equation, y equals root x plus 4 minus 1, and replace the y with x, which is to say, we would write x equals the root of x plus 4 minus 1. Because if the right side of the equation outputted the original input value, that would mean that both x and y were equivalent. I'll leave that as a bonus challenge for you. Back to the domain and range. To find the domain and range of the blue graph, we simply say that we are right of and above the endpoint, which is to say our domain is from -4 to infinity, and our range is from -1 to infinity. In order to determine the domain and range of the inverse relation, we don't need to use the graph. We can simply remember that the domain and the range of the original will simply exchange places. In order to determine the equation for the inverse, let's start by exchanging x and y. Now, we need to isolate y. This means we'll need to square both sides of the equation in order to eliminate the radical, or square root. However, we can't do that until we've isolated the square root. So let's start by adding 1 to each side. Now that we've isolated y, we seem to have a parabola. This goes well with what we had seen in our graph. However, our graph showed only half of the parabola. So how can we say that we want the points on the parabola, but we only want some of them? This is achieved by limiting the domain. We say we want the points on the green parabola, but only those that are right of or including an x value of -1. Our final class example, 1.55, will ask us to place restrictions on a function so that its inverse is also a function. This question isn't particularly challenging, but students often misunderstand what it's asking. Here, we've been given a parabola, f of x equals x plus 3 squared minus 2. It is a function. However, if we graph its inverse, we can see that it is not a function. This is because the original fails the horizontal line test, and consequently, the inverse fails the vertical line test. Now, students who misunderstand the question will think it's saying to restrict the domain of the inverse so it is a function. But that's not possible here unless we simply erase the entire function. However, we can place restrictions on the domain of the original blue graph such that the inverse will be a function. As an example, if we restricted the domain to only the right half of the parabola, then our blue graph would look like this. This is the domain of all values of x greater than or equal to 3. And as a result, the inverse, which is the green graph, would no longer fail the vertical line test. Now it is a function. However, this domain is not a unique solution. Another option would be for us to keep all points to the left of positive 3. We still have only half of a parabola, and so our inverse is, in this case, the bottom half, as though it were a negative radical function. But again, this is not the only other solution. Now, we could get crazy and creative and just start making up numbers. But what's important is you understand conceptually what's going on here. If we keep any part of both halves of the parabola, then our original graph will fail the horizontal line test and our inverse will fail the vertical line test. As long as we keep half the parabola or only a portion of that half, then we will pass the horizontal line test originally and the vertical line test in the inverse. So there are actually an infinite number of answers to this question. X could be greater than or equal to 3, greater than or equal to 4, greater than or equal to 5. It could even be between positive 3 and positive 5. However, it couldn't be an answer like x greater than or equal to 0, because that domain would still include some part of both the left and right half of the parabola. So again, as long as you are to the right of positive 3 with nothing left of it, or you are left of positive 3 with nothing to the right of it, you will have an inverse that is a function. Having said all of that, could you find a possible domain for part B so that its inverse would be a function? Here, I've listed 3 possible options that would limit the original graph in such a way that it would pass a horizontal line test. Notice in none of the options did I keep anything between positive 2 and positive 5. Because that section of the graph is a horizontal line, in the inverse it will always be a vertical line, which in itself would fail the vertical line test. However, keeping from negative 7 up to positive 2, or less than that, such as negative 1 to positive 2, or even that section on the right from 5 to 7, would all generate functions whose inverses would also be functions. A challenging question.